Welcome to tutorial 2 single phase system. In this question, we will look into using ideal gas mixture law to perform our mass balance calculation. So we have a question sounds like this. We have a fuel gas containing 86% of methane, 8% of ethane and 6% of propane by volume flows to a furnace at the volumetric flow rate of 1450 meter cube per hour at T equivalent to 288 Kelvin and P absolute at 2.48 atm. The fuel is burned with 8% excess air. Calculate the required flow rate of air in SCMH. SCMH is standard cubic meters per hour. Right, so this is basically a combustion problem. It's a combustion process, but in ideal gas state. But we are not having one single gas, but we have a mixture of ideal gas. So we are told to calculate the required flow rate of air in SCMH. That means we need to use the STP method to get our flow rate of air, the flow rate of air that goes into the furnace. Since it is a combustion process, because it's combustion, then we have to write down the equation for the reaction of combustion. So we know we have methane, we have ethane and also propane that reacts with oxygen. So we have to write down the equation for that, all the three compounds combustion, because we require this equation later. Right, at the same time, we have to draw our process flow diagram. So what actually is, because by drawing the process flow diagram, we actually can understand better what is the thing that we require from the question. So we know we have one furnace, we have volumetric flow rate of fuel, which is 1450 meter cube per hour, goes into furnace, one stream. And just now we are given that we have 86% based by volume percent of methane, 0.08% by volume of ethane, and 0.06 if in percent is 86% by volume of methane, 8% of methane, 86% is methane, 8% is ethane and 6% is propane. So if you have percent by volume, it is actually equal to mole fraction. Okay, if you in the questions you are given in terms of volume percentage, it is actually equals to the molar percentage. You can just use as a mole percent. And we are also given air, but we are given information that we have 8% of air. That's it. We do not have the volumetric flow rate or anything about air. So the question wants us to find the volumetric flow rate of air. Okay, using SCMH method, using the STP method. Okay, in order to find this volumetric of air, we actually need to find theoretical oxygen first, because if we find the theoretical oxygen, then we can link it to air. Okay, so in order to do this, we need to convert this volumetric flow rate into molar flow rate first. We know the volumetric flow rate of fuel is this value, so we need to convert this into the molar flow rate first, because we need to use that molar flow rate to find the molar flow rate of theoretical oxygen and also air later. Okay, now The question wants us to use the method of STP to do this calculation. So we know if STP, then we have to use this equation, still ideal gas law, but with reference of we using the value reference value. So we have this equation. If we are using the reference value, PV divide the PS specific molar volume of the standard equals to NT over T standard. So we know our specific molar volume for STP we have in one condition in cubic meter is 22.4 meter cube per kmol. This is what we know. So now let's find let's find the molar flow rate for this fuel. So now let's modify the standard formula just now so that we can find the molar flow rate for fuel. So when we readjust this equation, what we'll have is we'll get molar flow rate of fuel equivalent to P times V volumetric flow rate times the standard temperature divided by standard pressure, specific molar volume standard, and also times T. So we just plug in all the values into this equation, plug in all the values that we already know into this equation, then we'll obtain the molar flow rate of fuel. For fuel is 152.17 kmol per hour of fuel. That is the molar flow rate for fuel. Okay. This is a total molar flow rate of fuel from this. Okay, now let's find the molar flow rate for specifically for methane, specifically for ethane, and also specifically for propane, because all this value will help us to find the theoretical oxygen, because theoretical oxygen later will relate to the air required for the process. See, so this is how we calculate the molar flow rate from just methane. So we know just now the percentage of methane in that fuel is 86. As I mentioned just now, if you have in terms of 86 percent in terms of volume is equivalent to 86 mole percent. So you just change the unit just now from volume to mole. So you have 0.86 kmol methane per kmol times with the total molar flow rate. Then you'll obtain the just molar flow rate for methane. You do similar calculation, you'll obtain now molar flow rate for methane, ethane, and also for propane. I might mention it wrongly just now. This is for methane, yeah. Okay, so do the same calculation, quite the same method calculation. Then you obtain the flow rate for ethane and also propane. Sorry, a bit confusing with the names. Alright, so now you already obtained the number of mole for the compound in the fuel line, because this information will need to calculate the theoretical oxygen. From molar flow rate for each compound, now we calculate the theoretical number of mole of oxygen required from the process. Okay, so we know just now for number of mole of methane is 130.87 kmol per hour. So now to find the theoretical, we have to use the theoretical method of calculation. So this molar flow rate of methane times with this ratio obtained from your equation. Okay, so if we look at the equation, we require 1 kmol of methane to react with 2 kmol of oxygen to produce CO2 and also 2 mole of water. So this will be the oxygen required for the process number 1, methane. So this number of molar flow rate for ethane times with the ratio of methane, ethane and also oxygen from the equation, plus with propane. Molar flow rate for propane times with the ratio of required propane and oxygen in this reaction. So in the because we have 3 compounds, right? Because we have 3 compounds, that means we have to add in the requirement for oxygen for methane, requirement of oxygen for ethane, and requirement for oxygen of propane. So in total, we have 350 kmol per hour of O2. This is our theoretical. So if we have this number of mole of our methane, ethane, and propane, we require 350 kmol of O2 per hour in theory. However, we are given information our air is 8% in excess. Therefore, in order to find the actual volume, number of mole of air, molar flow rate of air, we know we have to do the next calculation. Molar flow rate of oxygen in is equal to 1.08 times by theoretical oxygen. So we obtain the actual amount of air, molar flow rate of air that goes into the process is 378 kmol per hour of air. O2. This is for theoretical oxygen. So this is calculation for theoretical oxygen. So the the actual oxygen that goes in, we have to use this calculation. We have 1.08. This 0.8 comes from the excess information. Okay, so this 1.08 times by theoretical oxygen that we have just now. So we obtain the actual mole of oxygen that goes into the furnace is actually 378 kmol per hour of oxygen. From this value, we use this equation where number of molar flow rate of air in equivalent to this actual oxygen divided by the 0.21, because this is the composition of oxygen in air. So you use this equation, you'll obtain the actual number of molar flow rate of air that goes into the process here. However, we have to remember the question wants for volume, the unit to be in meter cube per hour. So this is not our final answer yet. So now we need to convert into meter cube per hour. Right, so this is the equation. So the volumetric flow of air, okay, equal to the number of molar flow rate of air we obtained just now times by the specific molar volume, the standard at STP. We know this value is 22.4 meter cube per kmol. Okay, so equivalent to, this is the value that we obtained just now, molar flow rate of air, times by this value of STP, the volume, specific molar volume for STP. Then we obtain the final answer of this in terms of meter cube per hour. That is 40,320 meter cube per hour. That is our volumetric air. That's it for this question.